Last time we were talking about control systems. We talked about open loop control systems where you have something you're controlling and something that controls it and some kind of an input. So the controller, in this case, essentially translates what you want versus into some sort of signal that it sends into the device you're controlling. The problem with this is that you don't necessarily always get what you want, as in the case with the toaster example and the clothes dryer example. A closed loop control system is when you have some sort of a way to expose internal state or expose the the behavior of the plant, which then can be fed back into the controller. So in this case, you have a set point, and then you have this subtraction where you take the set point and you subtract the actual output from the plant. And then this creates an error signal, which is how far you are from your set point. And you feed that into the controller, and then you use that as the input to the controller to then control the plant. So in this case, the input into the plant is called a manipulated variable, and the value that's coming out of the plant that you're reading and you're using to subtract from the set point is called the process variable. And so this will allow you to adjust the input to the plant, the manipulated variable, as a function of the state of the plant. So a good controller will still work even when the plant is subjected to disturbances, like so in the case like of the toaster. The performance of the heating coils may not be exactly known at the time you design the controller, or maybe the temperature of the room somehow affects the performance of the toaster, or the different bread you put in it, varies in how long it takes to brown the bread. So those are disturbances. In the case of a drone controller, the disturbances would be like wind or some kind of external forces acting on the plant. So what you hope is the controller can still maintain control of the plant even with these disturbances, which kind of act like an unpredictable additional input into the plant. So I talked about some examples, and then we talked about linear time invariant systems. So this is one way that you can model both a controller and a plant as an LTI. An LTI is describes the dynamics. And so, as I mentioned, you can use this to model both the system and the controller. Or the physical system model, meaning the plant, and the controller, which is the thing that's controlling it. So an LTI is a linear differential equation, and so you've got these time series variables, which are signals, and you're allowed to multiply them by a constant. You can also multiply the derivative. The derivatives are integrals of those signals by a constant, and then just add them up. So that's why it's linear. Time invariant means that those coefficients are constants, they don't vary over time. So LTIs have a frequency response. You may be familiar with that from circuits. They can change if you're looking at the output of an LTI versus an input, they can change phase and amplitude of a signal, but not the frequency. So now the one thing that's a little confusing here is that you have an LTI that could be described as a time domain function. You can also describe it as an S domain function, frequency domain. In this case, your variables are usually capitalized, and then instead of being variables of t, they're variables of s. S is a complex variable. And but the transition going from the time domain to the S domain is easy. You basically convert your derivatives into multiplying the variable by S, and integrals is 1 over S. And so like the second integral would be 1 over S squared. Second derivative would be S squared. So it's fairly straightforward to go from an LTI in the time domain to an LTI in the S domain. Now, the problem here, one thing that's a bit confusing here is that this is an S domain description of U of S, right? It's a signal that's described in the frequency domain, right? This is not the same as a transfer function. A transfer function is when you rewrite this where you are looking at the output with respect to some input. So you have to decide what your output. See, this doesn't really have outputs and inputs. It's just a function, right? But if you create a transfer function, you have to rewrite it where you have the output is in the numerator, so the y of s in this case would be the output, u of s is the input, and that's the denominator. And so in this case, in order to restructure it into a transfer function, you're just using algebra. So you factor out y of s over here on the right-hand side of the equation, and you divide both sides by y of s. So you end up with u of s over y of s. And what you end up with is on the left-hand side, you have the variables, the signals, y of s and u of s as a ratio. And on the right-hand side, it's just a ratio of two polynomials of s. So there's no signals here on the right-hand side. So there's one input, one output. They're on the left-hand side. And then the transfer function is on the right-hand side of this equation. And it's a ratio of two polynomials of s. Now you might say, okay, well, yeah, but that's only one input and one output. What happens if there's like more than one input, more than one output? If that's the case, you actually have to build a matrix with these S polynomials in the entries of the matrix. Or you can use state space representation, which is another way to do this. But generally, in this case, in this class, we're just looking at single input, single output transfer functions. So the idea there is you take the big letters and then of S, like the signals, and you're moving them to one side as a ratio, and on the right-hand side, you just have this ratio of two polynomials. So that's a transfer function, whereas this is just a function, right? This just describes the dynamics of y and s. It's kind of set up to where u looks like it's the output here, but it's not. Actually, u is the way I made it actually the input down here in the transfer function, right? So in other words, that's a function and that's a transfer function. That's the difference. Okay, so the question is, what is the objective of a control system? Well, there's several objectives. One is that you're hoping to make the system behave a certain way. And that's why we're talking about it, because in this class, we were hoping to describe the practical aspects of building cyber-physical systems, which are any kind of computer that controls the outside world. So, robot controller, thermostat, drone controller, power electronics controller, things in the digital world, a processor that controls the physical world. And so in order to do that, you need control theory. And that's the idea. So we want to be able to have a computer that bends the wheel of the physical world, essentially makes some physical system do something. And specifically, what you're generally trying to do is you're trying to have it hit a set point, right? So you have a set point, that's the input. And then for a drone, this would be like, I want you to fly at an altitude of 50 meters. And then you have an actual altitude that comes back, and you're trying to make this error zero. You're trying to get the physical plant, the physical system to do what you want it to do. And that's the objective. But there's some other objectives, though. Another thing you want it to do is you want it to be stable. Because one of the problems with controllers is that they can be unstable. They can go into this thing where they oscillate bigger and bigger and bigger oscillations until they like if this were a drone and it became unstable, it would start overcorrecting and eventually fall out of the sky, right? So that would be if you hit instability. And so what you're hoping is that your controller guarantees stability. That's one thing. So in addition to making the physical world do what you want it to do, you don't want it to go unstable. So there's this notion of stability, or BIBO, which is bounded input, bounded output stability. As long as the input signal is stable, you're hoping that the output signal is stable as well. So I gave this example of in F-16, the physical flight surfaces and the aerodynamics of an F-16 by themselves are unstable, but when you combine them with a controller, it becomes stable. But in other words, you can't fly an F-16 with a physical connection between the controls and the flight surfaces. You have to have a controller in there in between that stabilizes the system. And there's a lot of cases that are like that. So the first question is, how do you know if a system is stable? And this is kind of a fundamental question. There's three ways that you can test it. You can hit it with an impulse response as the input, right, and see what happens. The second thing you can do is you can find the S-domain poles, and the third way is you can just simulate it, right? You can just run a simulation. Now, one thing I want to mention, I don't think I made this very clear last time, is that the reason why people use the impulse response here is, hold on, let me go back. Impulse response. Where's the impulse response? It's not there. Right there. So the impulse is an infinitely short input of 1 around time 0. Or it doesn't have to be time 0. It's usually at time 0. And then everywhere else it's 0. Now the problem is that that's not really practical in reality to have an impulse response. But the reason why that's used is because I mentioned last class it includes all the frequencies. It's basically, in order to create an impulse, you have to sum together an infinite number of frequencies. But also, the S-domain representation of an impulse is 1, is the constant 1. In the S-domain, 1 is the impulse. The step response, which is here, which is where you go from, you basically step to 1 at some point, right? Like in this case is at time 0. You go from 0 to 1 and you stay at 1. That's a step function. The step function in the S-domain is 1 over S, I believe. But it's more complicated, so it's easier just to use this impulse response. It has a Laplace representation of just the constant 1. So that's what I'm trying to show here. This delta it's delta of S equals 1. The reason I use delta is because the impulse is sometimes called the Dirac delta function. Okay, so what is the significance of that? Well, if it's because the S-domain function of the impulse is 1, then if you multiply the Dirac delta in the S-domain by a transfer function for a system that you're testing, basically the 1 kind of just disappears, and you end up with just the transfer function of the system. So what that means is that if you can take the transfer function and convert it to the time domain, you get the impulse response for free, right? And so that's what we talked about last time. So really what you're doing is you're multiplying the Dirac delta, which is just 1, by the transfer function. If you convert that to time domain, you get the impulse response. So we have an example here. And this is actually, So we have a transfer function y of s over u of s, so y is the output, u is the input, and the transfer function is 1 over 1 plus x minus 6x to s to the negative first power. And you need to get this into a form where you can factor the denominator. So we factored it's s plus 3n minus 2, and this is just using algebra. And then because you have the denominator factored, you can find the values of s that will give you a divide by 0. That will make the denominator 0, and those are the poles. And so in this case, s equals minus 3 and s equals positive 2 are the two poles. Now I mentioned that s is a complex number. So in this case, the poles are they have an imaginary component of 0 and a real component of negative 3 and positive 2. And so those are your two poles if you plot them on a plot where the imaginary number is the vertical axis and the real number is the horizontal axis. Obviously, those are just on the horizontal axis, negative 3 and plus 2. And because of this plus 2, you end up with a pole that's outside of the left-hand side of this plot. And so for that reason, it's an unstable transfer function. Now, again, it's not necessarily always unstable. You can hit it with certain frequencies where it will be stable, but if there are some frequencies that you can inject in there that will cause it to be unstable. And I think 2 radians per second is the one that'll do that. And then one way you can see that is if if you don't want to take my word for it, the way that you can test this or see what happens with the impulse response, at least, is you can convert it into a form where you can do the inverse Laplace transform. And in order to do that, you have to get it into a form where you've got these clauses of some constant over s minus a. So you take this and you convert it into 3/5 over s plus 3 plus 2/5 over s minus 2, just using algebra. I talked about that last time. And by the way, this only works because these two roots are unique. It's not always straightforward to do this. But we found these s plus 3 and s minus 2 denominators, and then we can convert this. We could do the inverse Laplace transform and get the time domain 0.6e minus 3t plus 0.4e to the 2t, this is called the eigenfunctions. And then if you plot that, you get this exponential curve, right? So this is actually the impulse response. Now you might say, well, wait a minute, I thought you started with the time domain version of this, which was just a differential equation. Yeah. So the idea is that I started with the time domain differential equation, we converted to S domain, then we made it a transfer function, then we did the inverse Laplace transform on the transfer function to get the impulse response. Right? This is why we didn't arrive back at the original equation, because we were using the transfer function. So the transfer, now you might, and again, I just took the transfer function and converted it directly into the time domain, which you can do because the impulse is just a 1. Right? If I wanted to look at the step response, I would have had to do the same thing, but I think multiply it by, 1 over s first. The other approach, of course, is you can just simulate it, which I think is also a common approach. So this is a MATLAB Simulink simulation of this thing. So I hit it with a step function in this case, and I created in MATLAB, you can just create a transfer function. You just tell it what the coefficients are of the polynomials in the numerator and denominator. And then you just hit the simulate button. Well, you have to tell it how long you want to simulate. So I said 10 seconds. And I should have said more than 10 seconds, because if you run it for more than 10 seconds, this wave continues to build infinitely. But it gets really big really fast. So I kind of just zoomed in on 10 seconds. But it only took 10 seconds to kind of build up very noticeably here. And you can see that it's responding in an unstable way to this step function. So I gave another example last time where, this is the sine wave input. There was another example where I tweaked the transfer function just a little bit so I could make it stable by essentially changing the denominator so the roots are both negative. And if the roots are negative, if all the roots are the poles, roots of the denominator are the poles. If the poles are all negative, then, or at least negative in their real component, doesn't matter, the imaginary component doesn't matter. But if the real component is negative, then it's stable. And then I did the same process, and you can see that's the step response there. A step response stabilizes there around 0. And so I also did this in MATLAB. You might say, why didn't you do the step response in MATLAB? I don't think you can, actually. MATLAB, I don't know how to do the step response. The impulse response. I don't know how to get it to do the impulse. But the step function is another convenient way to do that. So instead of hitting it with the impulse, I hit it with the step. And you can see that, it kind of behaves in a similar way as the impulse. It kind of jumps up here and then it just settles back down. And so all I had to do to make it stable was ensure that the poles were both negative or have a real component that's negative. And there's a sine wave. You can see that this thing's actually a filter now. This is a filter that is attenuating. So you give it 2 radians per second input, and with an amplitude of 1, and frequency that comes out is the same, except the frequency is 0.2. So what I ended up doing here was creating some kind of filter that attenuated my input frequency. Presumably it would attenuate some frequencies and not others, but I'm not looking at the frequency response here. I'm just looking at a sample input. Okay, so and I mentioned that transfer functions are nice because you can connect them together like building blocks. So I don't know if you guys ever use Simulink, but basically that's the idea of Simulink. It's kind of like a CAD tool. You can put building blocks together, and those building blocks are models of whatever. One of the ways to build the model is an S-domain. You could also use state space. There's other ways to build it as well, but these transfer functions are like building blocks that make it easy to compose systems together. Because if you connect one into another, the resultant transfer function from the input to the first block to the output of the second block when they're connected in series like this is just the product of the transfer functions, which makes sense algebraically, because if this one is y of s over u of s, and this one is g of s over y of s, then when you multiply these together, the y of s just gets canceled out, right? And so you end up with g of s over u of s. So that's a pretty natural way to compose these systems. So I mentioned that you can, just to give you an example of a physical system model, this would be a plant. This would be building a plant model. In this case, I want to just take a coin and just push it. So the input to the system is a force, which is u. The position is y. That's how fast I pushed it. And then we have some parameters. Mass of the coin is m. And b is the coefficient of friction. So the way the friction works is that the b is, if you take b, the friction, and you multiply it by the velocity of the coin, which is the derivative of y, which is shown here as y dot. This is just a notational thing. So instead of saying, dy of dt, I just say y dot, right? So y dot is the first derivative, and y dot dot is the second derivative. So if I take the force and the friction, if you multiply the friction by the velocity, you get a counter force. So you subtract that from the input force, and that needs to equal the force of the coin as it moves, which is the mass of the coin times the acceleration of the coin. So this is something I'm not expecting you to be able to build these kind of things, but I just want to give you a real simple practical example. This is something that obviously you would do like in a physics class. But the idea is that you create an equation of motion for the coin, which relates the force I put into moving it to the actual position. So if you can just come up with and you could do this for a spring. It's also a very similar type situation. But basically, you create this equation, and then you transform it into a transfer function, which relates y to u. And so in this case, if I do that, I convert everything to the S domain, I end up with 1 over m over S times S plus B over m. So it's a really simple transfer function. It just basically tells you where the coin is as I apply a force. The problem is that, yeah, that's the coin, force, and that's the y, the position. So the idea is I want to build a controller that will move it to a set point. So this is kind of like a robotics thing, right? Where, like, say I want to have a robot that moves this coin and stops it at a specific spot. And so I have some set point I want to reach, right? The problem is that it's actually unstable, which is kind of crazy, but it's kind of hard to imagine this, but if you hit it with a step, what happens is that if you change the force instantaneously from 0 to 1, it'll like shoot the coin off. And so it's technically unstable. It's kind of hard to believe, but even that simple system is unstable. Okay, so the objective is to build a closed loop controller for this. Now this is where things get a little weird, because I mentioned to you that if you have multiple components, transfer functions, and they're connected in series, you just multiply them, right? But then how do you do this? How do you do the closed loop feedback control? That part's a little tricky. The reason is because if this is the controller and this is the plant, these guys are connected in series, and these are both transfer functions, presumably. You have transfer functions for both. But this y is where the coin is. This is not a transfer function. This is a signal, right? It's a time series signal or a frequency domain signal, right? Likewise, the error is just a signal. It's a function, an S-domain function. So you've got two transfer functions in here, but you've got it mixed in with these two like variables, basically, right? And then you've got ref. This is your set point, right? And your set point is AC. You can change it. It's dynamic, right? Like if I have a robot, I may want to have him continuously, change the position of the coin, and he has to figure out how much force to apply, right? So you've got basically three variables, and you've got two transfer functions. So what I really want here is I want a transfer function that relates y as the output and ref as the input, right? So I want to build a transfer function for this whole closed loop system where the output is y and the input is ref. Ref is the set point where I want it to put the coin. Does that make sense? And then once I have that transfer function, I could check to see if it's stable. All right? And if it's stable, then I can also check other things like how long does it take to reach the set point? And how far do I overshoot? Right? I could check. There's other performance factors that you're interested in with control design. Like how good's the controller? Well, it's stable, but it takes a while to get to the set point, right? So those are the things we want to know. So first we have to build the transfer function. So this is a little strange. Try to follow me here. So I'm using some shorthand here, by the way, too. So YCL is this function, is this signal, and that equals the product of the GP, GC transfer functions. Now, these are shorthand, by the way. These are shorthand because GP is actually GP over GC, right? It's a ratio, right? But I'm not showing the ratio. I just say GP, it's shorthand, right? Likewise, GC is GC over whatever the input is, E of S, right? So I'm using this shorthand where I just multiply these two transfer functions. And then the input here is ref minus YCL. Okay, that is the thing, the next thing in the chain, and it wraps around. Okay, so you can just essentially at that point, your goal is to just use algebra to figure out to rewrite this as YCL over ref. I mean, that's the goal, right? That's really all you have to do here. So I distributed this out, and then the right-hand side of the equation there. And then I got ref isolated over here on the right-hand side. So I basically added this term to both sides. And then we take out YCL. So I divide YCL out of this side. So it's YCL plus 1 over GPGC equals GPGC RREF. Okay, so now I've got YCL by itself. And then you just have to divide both sides by 1 plus GPGC. Okay? And then divide both sides by RREF. So what you end up with is YCL over RREF equals GPGC over 1 plus GPGC. Now this is actually a classic closed loop form. And the idea is that if you have the controller connected to the plant and they're in open loop configuration, the open loop transfer function is just these two multiplied, right? That's it. But if you want them to be a closed loop system, then it's the open loop transfer function divided by 1 plus the open loop transfer function. And that's really all you have to remember here. This is just the derivation of that. But that's all you have to remember. That's the closed loop transfer function for this loop. Okay, so what about the controller then? How do you create the controller? Because we have the plant model, which is a just physics model, right? It's a physics model converted to Laplace and then turned into a transfer function, right? That's what we did for the plant. What about the controller? So for the controller, one of the most common types of controller is a PID controller. You guys, I think you covered this in robotics. So a PID controller is a proportional integral derivative controller. And so you basically, you can have a coefficient that you multiply against the error that's proportional. And then you have a coefficient, that's K sub P. I don't know what K is, but P is the proportional coefficient. D is the derivative coefficient. You multiply that by the derivative of the error. And of course, the error is the input to the controller. And then the integral is, obviously multiplied by the integral of the error. So you have the error, the derivative of the error, and the integral of the error. And then you have coefficients that multiply against each one. And so why do you do this? Well, the proportional is you want to basically, as you approach the set point, the idea is you want to kind of slow down. And then the integral is when you want to add more correction. You want to strengthen the output of the controller when the longer you have error, the longer the error persists. That's kind of the idea, right? And so if you have a PID controller, you can express it really easily in the time domain. It's just, Kp times the error plus Kd times the derivative of the error plus Ki times the integral of the error. It's trivial then to convert this to S domain because you just, pretty much just the derivative is just S. And the integral is 1 over S, right? So you just make that replacement, and then you can convert this into a ratio of two polynomials. So now, by the way, somehow I dropped the error out of here. Sorry. So this is E of t. It should have been E of S down here, and then you'd bring the E of S as the denominator here. So I was a little sloppy here. But each of these, when you go from time domain to Laplace domain, the lowercase e of t will become an uppercase E of S, right? And then you would just divide that and make it the denominator here. But you end up with the transfer function ends up being a ratio of two polynomials, which is kds squared plus kps plus ki. So basically the idea is you multiply this times s over s, which makes the 1 over s ki be the last term here, ki, right? And so you have a denominator here of s. So the problem is that, as you might imagine, this transfer function is also unstable because the pole is 0. There's a pole at 0, right? S equals 0. So this is unstable. So we know the plant is unstable and the controller is unstable. But if you put them together, you're hoping they'll be stable, right? Now the problem though is, oh, and by the way, sometimes you don't need all P, I, and D. So in this case, we'll simplify it. We'll drop the derivative and we'll just use a proportional integral controller. I did this just so it simplifies the math. So in this case, I have a new one here. This is a PI controller. Basically, I just dropped the derivative. So this is K, so the S square term in the denominator is now gone. So it's KP times S plus KI over S, right? Again, though, it's also unstable. And so if I hook everything together, I can calculate my open loop transfer function, which is just the plant multiplied by the controller. Sorry, the controller multiplied by the plant. Make sense? So this will give me the open loop transfer function. Now the problem is that I haven't assigned values to Ki and Kp yet. Those are, so normally you would tune those. Did you guys tune those in robotics, right? You just kind of arbitrarily guessed what those should be. In this lecture, I'm going to try to come up with good values analytically. I am going to set B to 1 and M to 1, though, the mass and the friction for the coin to 1. So I'm going to set those arbitrarily. So once you set those, you get the following total transfer function, open loop transfer function, KPS plus KI over S squared times S plus 1. Okay, so the poles are at 0 and -1. So that's actually unstable, right? So the open loop transfer function is unstable. What about the closed loop transfer function? Well, the closed loop transfer function is the open loop over 1 plus the open loop. So you can see that this starts to get a little overwhelming. So I tried to simplify that. Okay, so how do you simplify that? It was just a bunch of algebra. So I multiplied the numerator and or I multiplied the denominator by S squared. Sorry, no, this 1, I made it S squared times S plus 1 over S squared plus S times 1 to get a common denominator here. And then once I had that, then I could factor out the common denominator on the numerator and denominator, which gives you this, and you end up with simplifying it to this. Okay, so that's it. So the closed loop transfer function is here. The problem is that I don't know if it's stable or unstable, because the problem is now is that Kp and Ki are part of the denominator, and those are going to determine the stability, right? So in other words, if I choose good PID coefficients, it could be stable. If I choose bad ones, it could be unstable, right? So now it's up to me. So I actually, I don't know the best way to do this. In fact, there's tools to help you do this. MATLAB has tools to help you find these. Or you can just guess. I tried to figure out a way to do it. I don't think this is the best way to do it. But so my approach was to basically say, okay, if you have, I mean, this is a third degree polynomial, right? So I'm assuming that I can factor that third degree polynomial as S plus A, whatever A is, S plus B, S plus C, multiplied, right? And if you do this and you leave A, B, and now again, this does not relate to that at all. This is just a general idea where I have S plus A plus S plus B times, I'm sorry, S plus A times S plus B times S plus C. If I expand this out, it's S cubed plus ABCS squared plus AB plus AC plus BCS plus ABC. This is just pure just algebra, right? Then I said, okay, well, let's say that I want to now take this, and now I want to match it up to what I have in the denominator. And the idea is that I want as long as A, B, and C are positive integers, then my roots will be negative. We'll have the real component will be negative. Again, S is a complex number technically, right? So S cubed, we know that's going to have a coefficient of 1, assuming I can factor it like this. S squared, now S squared is S squared coefficient is going to be A plus B plus C. So my coefficient for S squared was 1. So I know that I'm going to set A plus B plus C equals 1, right? And then the coefficient to S is Kp, which I know, so that's going to be A times B plus A times C plus B times C. That's going to be my coefficient for S, which is K sub P. So I'll set that to K sub P. And then the coefficient for S to the 0th power is going to be Ki, which is just going to be A times B times C, right? So now I have 3 equations and 3 unknowns. And the idea is if I can solve this, I can come up with, well, if I can find values that will work here, then I can also come up with values for Kp, Ki. So A plus B plus C, I think I just guessed, right? If I said 0.25, 0.25, 0.5, right? That adds up to 1, right? Now, if I set those values, so I pick 3 values that add up to 1, and then, and I make sure they're positive, by the way, right? I want them to be positive because that'll give me negative poles, right? Then I can then figure out what Kp should be and Ki by just multiplying these guys out. So what I got there was Kp is 0.3125 and Ki is 0.0313. This is not the accepted way to do this, by the way. This was my own approach to come up with this, right? So I set those guys up, and then I went ahead and plugged those in. So now I have the impulse response for the closed loop control, right? I plugged them in. And then I hit it with a step. And the step function looks like that. So now you might say, wait a minute. What is the step? Is that the step or is that the impulse? That's actually the impulse. That's the impulse. I guess I did get the impulse. Yeah, that's the impulse. But anyway, the point is that the impulse is stable, right? So the whole system is stable. That means I don't have to worry about giving it a frequency that blows it up, that causes it to oscillate out of control. So that's good. But then let's think about this, though. What does this actually represent, though? Like, what is this input? This is the set point. So this is equivalent to me telling the robot hand that's moving the coin, I want you to move the coin up and then move it back down instantly, right? And if I do that, this is actually the way the coin will move in response to that command to the controller, right? Now that's kind of a dumb command because it'd be more likely it would be a real step response. Yeah, so here's the step response. So this is like, okay, robot, don't move the coin. Now I want you to move it 1 meter, right? And so you can see that what the robot will do, the controller, is it'll move the coin, but it overshoots. It goes too far. And then it kind of corrects down and then eventually hits the position, right? So this works. It's stable. It achieved the goal, but it didn't perform that well because it took like 40, actually I don't know if you noticed, but when I first showed these plots I had 10 seconds of simulation. This is a 40 seconds. It took the robot 40 seconds to get the coin to move 1 meter, which kind of stinks. I mean, so this is called the overshoot, and that's the rise time. And so a good controller will have you're going to minimize the rise time. You want it to get to the set point as quickly as possible, and you want to minimize the overshoot, right? So how do you do that? Well, as you guys know from robotics, you have to kind of tweak those values. So if I increase the proportional response to 1.25, so this is the original and this is the new, increasing the proportional coefficient. Now, by the way, if I do this, I risk making the system unstable, by the way, if I play with this stuff, right? But I just threw caution to the wind here, and I said, look, I'm just gonna try stuff. So I increased the proportional response to get it up to the set point faster. And that worked pretty well, actually, because that's that overshoot is about the same as it was. But then I thought, well, can I fix the overshoot? What if I increase the integral coefficient to 0.3130? And that actually made it worse. that made the overshoot even worse. So, but again, I don't know. I don't really know how else to play with these numbers to get this thing to work better, or even to guarantee that it's stable for that matter, other than going back and rechecking the transfer function. So that's a little dicey, but that's, adjusting these things outside the scope of the course. I just want you to understand the concept and the limitations. Yeah, the other thing is kind of interesting is that this blue line is the input. That's what I want the robot to do. That's the set point. The yellow line is where the coin is. But one thing I didn't show was the actual force, right? I didn't show there's an internal signal that I'm not showing, right? The internal signal here is there's the reference, which is the yellow line, right? Then there's the output of the process variable, which is where the coin is, right? That was the other line I showed you. But I never actually showed you that. That's the force, that's the manipulated variable that the plant is, the controller is sending the plant. I didn't show you that, so I thought it would be cool to look at that too. So that's what that orange line is. Just because I thought it was kind of a neat, all right, so the blue line is the set point, the yellow line is the position. This is what the robot's actually doing now. This is the force it's putting on it. So it exerts this enormous force, and then it kind of pulls it down and goes negative to pull it back. And of course, that's because there's that overshoot. And then eventually it stabilizes at 0. Well, that makes sense, right? Because once the coin gets to the set point, the force should be 0, right? So I thought that was kind of cool. And then there's a, you can give it a sign input too. Okay, so that's basic S-domain control theory. But the problem is that S-domain is continuous, and you can't actually build a continuous controller on a processor. It's impossible. You have to build a discrete controller. And so there's this whole separate concept called the Z-domain for discrete controllers. You can't actually build an S-domain system digitally. You can't build a controller that's S-domain controller unless it's an analog system. Like like if you have a greenhouse, in the greenhouse you want to control the temperature in the greenhouse, and the way you do it is you open louvers. And if you design those louvers to respond to heat, like the metal on the louvers expands when they get hotter and it opens them, and that cools the greenhouse, and then when the greenhouse cools, the metal contracts and they that would be an actual continuous controller, right? But a processor can't do that. And you might say, wait a minute, but you simulated it in MATLAB. Yeah, because MATLAB discretized it, right? It's actually lying to you. It's doing a discrete simulation. So how does that work? Well, that's called the Z domain as opposed to the S domain. And so Z is a way to go from time domain to the Z domain. It's similar to going to the S domain, except it's the discrete. But there's a few important differences. The first thing is that if you have a signal called x of z, you know, like if you have S of Z, or X of S, for instance, in the S domain, if you multiply that by Z to the minus first power, what does that mean? What does that signify? Have you guys seen that notation? Z minus 1? That actually represents the signal delayed by one time step, where the time step is the discrete time steps that you're simulating with. Like, for example, the clock period, clock tick, right? So in other words, if you're building this in digital logic, like a Verilog circuit, this would be like just saying always at pause edge clock and then setting something. It puts a 1 cycle delay, right? That's what this does. Z minus 1 is a 1 clock cycle delay. It's a register. It's equivalent to like a register in a circuit. Likewise, if you say Z to the minus 7th power multiplied by X of Z, that's delaying the signal by 7 samples, 7 periods. Make sense? Now another notation, in the time domain, they usually say X of N with brackets, which is the time domain. You might say, why N and not T? Because N is the sample number. Which sample number? Like which clock cycle number, right? As opposed to it's a discrete version of time. Okay, anyway, so if X of N is the current time, then X N minus 1 is the previous cycle, previous sample, and X N minus 7 is 7 samples back into the past. Okay, so the objective here is like if you have a continuous system, this is a little blurry, sorry. If you have a continuous system that looks like this, when you discretize it, you're basically dividing the time into samples, and the samples are like vertical delineations on a time plot, time scale, where the horizontal axis is time, the vertical axis is the value. And this is actually one way to do it. This isn't the only way to do it, by the way. This is called a zero order hold, which means that at every time step, you basically set the time domain, you set the discrete time domain signal to whatever the continuous signal was. And then you hold it throughout the whole time, right? Until the next sample, and then you go up to whatever the continuous signal is there, and you hold it, right? So that's a zero order hold. That's not the only way to do this, though. You can also do, like instead of doing it this way, you could set it up to where this guy, the continuous signal, crosses at the midpoint, right? But the simplest way to visualize it is a zero order hold, right? Where basically you just have these discrete time steps, and you set the signal to intersect the continuous signal at each time step. So you end up with this little, discretized version of the signal, right? So this is the continuous signal, and this is the red line. The black line is the continuous one. The red line there is the discrete. Okay, so what about the Z domain, though? What's that all about? So if you have a time domain, the idea here is that if you have a time domain continuous differential equation, you can convert it to the Z domain. And in the process of doing that, you're also discretizing it. Does that make sense? So the Z has rules similar to the S domain in terms of determining if it's stable. If the transfer, like you can build a transfer function in the Z domain like you can in the S domain. And the stability rules are similar, but not exactly the same. It's not just looking at the poles being negative. A system that has poles that are close to the origin of the pole and zero plot, right? Or the pole plot, will settle rapidly. A system with poles that are close to the unit circle will settle slowly. Again, unit circle meaning Z is a complex number, you're plotting it just as an XY plot. And if you're around the unit circle, the system will settle slowly if the poles are on the unit circle, which means they can be positive. unlike S domain. You can have positive poles and still be stable. A system with poles right of the unit circle may have sustained response, or with certain bounded inputs may have an ever-growing response. Well, that's kind of flaky. That's kind of uncertain. And system with poles outside the unit circle have a response that grows exponentially. So the rules for the Z-domain stability are a little bit more flaky than they are for the S-domain rules. Okay, so let's look at an example here. So let's say you have a continuous differential equation, LTI, linear time invariant system. So this is the same example I showed before. U of t equals y of t plus derivative of y minus 6 times the integral of y. Okay, and then you can convert this to S domain very easily. Now, over on the discrete side, what you're looking at here is the y. So you have u of k and y of k being replaced for u of t and y of t. Now, but for the derivative is a little different and discrete. In this case, the derivative is the y of k, which is the current sample, minus the previous sample, y of k minus 1. So that's the change from the last sample. And then for the integral becomes a summation where you're summing up all the samples from, in this case, instead of time 0 to t, I equals 0 to k, and you sum everything up, right? So the integral is summing all the samples, whereas the derivative is looking at the difference between the current sample and the previous sample, right? So now when you go to the Z domain, and this is where things get really wacky, when you do the derivative in the Z domain is when you take the variable y of z, that's the variable you're taking the derivative of, and you multiply it by z minus 1 over z. Does that make sense? Well, it turns out, like, check this out. Z minus 1 over z is equivalent to saying 1 minus 1 over z, right? And 1 minus 1 over z is like saying 1 minus z minus 1. It's 1 minus z to the negative first power, right? Well, that's what you're doing here, because remember I said that z to the negative first power is the previous sample. So if I take 1 minus z to the negative first power and I multiply it by y of z, that's like saying the current sample minus the previous sample, right? It's the same thing I'm saying here. It's equivalent, right? It's just doing it with this fancy z notation. Okay, but then the summation is actually replaced with z over z minus 1. Now that one is weirder. Why is it z over z minus 1? It's because if you take z minus 1 and you keep dividing it into z, what you end up with is an infinite sequence of 1 plus z minus 1 plus z minus 2 plus z minus 3 plus z minus 4 infinitely. Right? So basically, if you expand this out, z over z minus 1, if you expand it, if you divide it out, you end up with an infinite sequence that's adding up all the previous samples. So that's the reason they do that. Okay, so yeah, so then you can take that, and once you have it in that form, you can do some algebra in order to factor out the y of z, which is just multiplied by each of the terms on the right-hand side. Divide it by both sides so you get a ratio, and you end up with a transfer function. Excuse me. So now we have a transfer function, u versus y, and then once you have a transfer function, you can convert it into a form. And this is just, sorry, I just keep converting it to try to get it to the point where I can factor the denominator. Yeah, is that it? There we go. So this was just to get it to the point where I could factor the denominator. This is just algebra. And I eventually get to here, and so you can see the poles, I finally have poles. -1 and 1/4. So what does that mean? if you go back to the previous slide and interpret what that means, this is on the unit circle, or close to it, right? I think so. May have a sustained response. What was that one? Yeah, system with poles right on the unit circle. Right, it's on the unit circle. So the interpretation is it may have a sustained response, or with certain bounded inputs, it may have a ever-growing response. So sustained response means what? Stable. Ever-growing response means unstable. So that really means nothing. It means it could be stable or unstable, we don't know. So that's actually kind of useless, actually, for determining stability. So that's no good. So I don't know. I don't know what to make of that. I don't know. It's hard to tell. Z-domain derivative, as I mentioned, I showed you this before, but if you have a derivative in the z-domain, it's z minus 1 over z multiplied by the variable you're taking the derivative of, right? The signal. So I mentioned that if you expand this out, it's just 1 minus z to the negative first, which is really just saying the current sample minus the previous sample, which is, as you think, that's the derivative, right? It's the current sample. It's the difference between the current sample and the previous sample, right? The integral, on the other hand, is z over z minus 1. And I mentioned that if you do long division here and you start dividing this, so z minus 1 divided into z, right? That's 1, right? But then there's a remainder, right? That's 1, and then I subtract z minus 1, right? And that's going to get a remainder of 1, right? So I have 1 remainder. Now if I take this and divide it into that remainder again, so that gives me just 1 plus 1 over z minus 1, right? So then if I take z minus 1 and divide it into 1, so like basically I have this and I get that remainder. If I take this expression and I divide it again, so now z minus 1 into 1, that gives me a quotient of z to the negative first power with a remainder of z to the negative first power. Right? So now I have quotient plus remainder right there. So now if I take z minus 1 and divide it into that, I get z to the negative second power with the remainder of z to the negative second. So basically, you keep doing this over and over again, and what you end up with is, like I said, it's just a repeating pattern. It's just z over z minus 1 equals 1 plus z to the negative first plus z to this negative second plus this, which if you divide this out, you're going to get z to the negative third with a remainder of z to the negative fourth, which is z to the negative fourth over z minus 1. If you do that, if you keep dividing it, you basically just get this infinite sequence, which, if you look at this, all you're doing is a summation, because you're going to take the current sample plus the previous sample plus the 2 samples ago plus 3 samples ago plus 4 samples ago. You're just adding up. You're just doing a summation, right? Again, assuming that you're treating z to the minus n as the sample that you received n clock cycles ago or n samples ago, right? So it kind of makes sense why this is the integral, why this expression is the integral. Yeah, so that's essentially what you get. It's the same as the integral. Okay, so now what about, okay, so what are we using the z for? Like, what's the point here? The point is that when you create a controller, what are you creating it for? You're usually creating for physics, a real physical system, which is an analog world. It's a continuous world, right? And then how do you, so the model is a S-domain. What's the controller? Is it S-domain? Well, sometimes, yeah. That's one way to do it, is you design a controller in the S-domain. for a physical world that's in the S domain. But then you have to deploy it on a computer. So you convert it to Z domain. So the question is, how do we convert S domain to Z domain? Is there a way to do that? Now, is that how people do it? That's one way to do it. That's one way to do it. I think most people, when they design controllers, they use tools. They use like CAD tools. They use automated programs that figure all this out. But if you wanted to solve it, if you wanted to do it by hand with a paper and pencil, this is how you would do it. You would have you'd come up with the physics for the model, then you'd come up with a controller design, which would probably be a PID controller. You'd have to tune that, make sure it's stable, and then you could look at the step response, right, and the impulse response, which is the eigenfunctions, right? You calculate the eigenfunctions. And then, if you want to deploy this on a computer, you have to make it discrete, and so you're going to have to go to Z domain, okay? So the problem then is that when you go to, if you have a stable controller in the S domain, is it still going to be stable in the time domain, in the discrete, in the Z domain? If it's stable in the S domain, is it stable in the Z domain? Well, actually, it depends on this, T sub S. That's your time step. And what's the time step? It's how fast you make decisions, control decisions. It's how fast you look at the process variables and calculate the manipulated variable. That's what the plant does, right? It reads the process variables, it calculates the manipulated variable, and puts it out. And the rate at which you do that is, or the time you have to do that is TS. So if you have a stable controller in the S domain and you convert it to the Z domain, you have to choose a T sub S. If that T sub S is, and how do you choose it? Well, it's how fast is your computer. How fast is your processor? Do you have an FPGA? Or do you have a processor? Like, what are you doing? Is this Arduino, Raspberry Pi? You have to choose that, right? Once you choose that, then if it's too big, the system may go unstable. It may fall apart, right? So how does this work? Well, first of all, you have to pick a transform. There's multiple transforms. The best one I found is called the Tustin transform. The Tustin transform is where you basically just, if you have an S domain transfer function, you substitute S for 2 over T sub S times T Z minus 1 over Z plus 1. Right? Now check this out, by the way. This is the Tustin transform in action. So this yellow line is the continuous line. And the Tustin transform of it is the orange line, right? Pretty cool, right? Except that's not what I showed before. Remember I showed you the zero order hold, where basically the step would come up to meet the yellow line. Notice that this yellow line intersects this orange line in the middle, right? That's because this is not the zero order hold. The zero order hold is another way to do this. But the Tustin transform is better in the sense that it gives you more of the discrete line tracks the continuous line a little bit more. So I picked the Tustin transform as opposed to the zero order hold for this. Either way, you're converting, continuous to discrete. And then the time step here was 1 second. I chose TS of 1, just to simplify things there. Okay, so let's see. Okay, so by the way, 1 over S. 1 over S. What is 1 over S? That's not a ramp. 1 over S is the step, isn't it? Yeah. Sorry, yeah, this is 1 over S, is this blue line here is 1 over S. I don't know, yeah, what was I converting here? Anyway, here's another one. Let's go back to the physical model of the little robot model thing. So remember the physical model for moving a coin across the floor is 1 over m times s squared plus bs, where m is the mass of the coin, b is the coefficient of friction. And and then this was the plant model, and yeah, that was the plant model. I don't know. Oh yeah, and this is, I just chose M1 and B1 here, right? I set M and B to 1, so you end up with this. So just this, right? 1 over S squared plus S. if you convert this using the Tustin transform, you get this. So you can see it becomes complicated really fast because you have to substitute that in for S to get there. So now I'm in the Z domain, right? So now I'm also going to set TS to 1 second, my time step. And so there we go with that. And then I'm going to try to factor this out so I can get I want to get it in the form where I just have, I want the denominator to be a factored polynomial. So I had to go through all this stuff. So now I have my roots. Now notice, remember, this guy had, originally, he had poles. The poles of this guy in the S domain was 0 and -1. 0 and -1, right? So he was unstable. But now in the Z domain, the poles are much different. The poles are at 1 and 1/3. So what does that mean? Well, I don't know, because it's harder to tell if it's stable in the Z domain. So how would we build this in C code? Well, the problem now is we have this guy, and if we can convert this back into the time, we don't want to go to the time domain. We want to stay in the Z domain, but we want to get it into a form where instead of it being a ratio of 2 polynomials, which is the way that we check for stability, right? You can use algebra and convert it into a form where the output, which is y in this case, is a function of the input, but the input and the output, right, rather, except you want all of the z exponents to be negative, not positive. Now you might say, why? Because if they're positive, you don't have to do the future, right? If the z to the negative power means past, right? So really, I want to have a controller that calculates the output as a function of previous samples, right? So if you can get into that form, you can build a C implementation of this. So I basically got it to where I had y of z equals 1/6 times u of z. Remember, u is the input, okay? So this is the current input times 1/6 plus 1/3 times z minus 1 times u, meaning 1/3 times one sample will go on u, right? The prior sample, input sample, times 1/6 multiplied by 2 samples ago in the input. And now check this out. 4/3 times z to the negative 1 times y of z. Wait a minute, y of z is the output. How do I calculate an output as a function of the output? Well, I can, because that's the old output. That's the previous output that I calculated in the previous clock cycle, or the previous step, the previous scan, right? As long as all of the y sub z's are multiplied by a z of a negative exponent, it's fine. I can use it. I can use it for calculating my input. Now you might say, wait, time out. Wait a minute. I thought you had like an integral in there where you have to add up everything back from till time 0, right? Well, no, you actually don't. The way you're working around this is, the way the math works out is I'm looking at previous outputs, but only up to 2 samples ago, right? Notice that I never have to have that integral that takes me all the way back to time 0, right? All I have to look at, as long as I have the last output 2 outputs ago, the current input 1 input ago and 2 inputs ago, I'm golden. I can just deploy this directly into a C model by basically going from this back to time domain, where the time domain is essentially just using the z to the minus whatever to look up previous samples, right? So going from this to this is trivial once you have it in this form. Now, I still don't know if it's stable, but at least I have a C implementation of this thing. Okay, so I ran some simulations of this. So there's the step response. Now, remember, this is just the coin, right? And the coin is unstable. What happens when you hit the coin with an instantaneous force? It shoots off into space, which it still does in the Z domain, but you can see now it's obviously discretized. In the S domain, this is the original S domain version I showed you. Okay, so for the PI controller, you pretty much do the same thing. You know, you start out with the controller. You have you convert to the Z domain. Now, in this case, actually, I didn't what I did here is I actually did not. The way I converted to the Z domain here is instead of doing the Tustin transform, I basically just said, look, I know the P. The integral is just z over z minus 1, right? So I just literally went directly from the differential equation into the Z domain using the way that you do derivatives and integrals in the Z domain. And I applied that, and then so I got the transfer function for that. And then so the open loop transfer function now is the Z domain transfer function for the PI controller multiplied by the Z domain transfer function for the coin. The open loop transfer function is just the product. The closed loop transfer function, of course, is well, I didn't show that, but that's the open loop transfer function. So this is and then this is the closed, I didn't show that, did I? Yeah, well, the open loop is here. The closed loop would be this over 1 plus that, right? That's the closed loop transfer function. I don't know why I didn't show that there, but then I calculated the response of the closed loop transfer function in the Z domain, and it looks a lot different. It has a lot more oscillation. Remember that in the S domain, it just went up and overshot, and then it came down, right? In the Z domain, it's oscillating, but it's oscillating in like an 8-bit, discrete way, right? But it does work, but still takes a while. 40 seconds was the same amount of time I ran the discrete, the continuous one. The discrete one still took 40 seconds to get going on that coin, but there was a lot more oscillation. But it appears to be stable. You might say, how do you know it's always stable? Well, because it's a step. The step function means if it doesn't go unstable for a step, it will never go unstable. The step function has all the frequencies in it. Make sense? Okay, and that's all I've got. That's the whole. Yeah, and I make some adjustments to the K and the P values there to try to fix it. Actually, integral 0 proportional 0.5. That one looked pretty good, even with a time step of 1 second. Okay, but that's all I've got. So that's all the material for control systems. That was just a taste. I'm going to extend, I don't think you were here, I'm going to extend the lab till Monday. So I'll send, lab 3. Okay, sounds good. Thanks, guys.